and I want to go here. So this is like a little website I made. Well, quite a big website as well. There's quite a lot of stuff in here, and also a lot of stuff that isn't in here. So this is Cataphysics website. And then, so this is kind of the first paper I did, which is in the Canadian journal that I've talked to you about. I've applied, I'd have to think about it. My brain's gone blank at the moment. So these are the different operators, and you have like just the basic operators that lead to.
Let me get, excuse me.
This one. There is a paper called Reimagining Complex Numbers. And that is basically the same info as here, right?
It's called the complex numbers, reimagining complex. Okay.
Yes. Let me see.
Okay, can go ahead, yeah.
Right, so these are the operators here. Here you have, it basically runs along the same line as, so XOR multiplication. So a plus with a plus is a plus, minus with a plus is a minus, and so forth. But then so that's like a logic gate. And then the XNOR version is just the inverse of that. And so this allows you to reclaim the rules of imaginary numbers. So like in this case, a plus by a plus is a minus. So they're just like, that's just a little quantum kind of operator system, because imaginary numbers are in use on the quantum scale. And I mean, in some ways they're just there because of the wave function, but then, you know, you could look at it as being more fundamental than that. And I think Sabine also has a video on a paper that was written, but hasn't been peer reviewed or anything, but they're kind of looking to the idea that maybe this kind of logic or something to do with them, just that the imaginary number I is sort of intrinsically in there. And I think that would be correct anyway, because if you're looking at probabilities, I mean, the wave function is a probability wave function, you know? And then you have the Pauli matrices, which are again spin matrices, and that will have to do with probabilities as well. And one of the matrices is the number I think, in certain, or it's very close to anyway. So they're all kind of in there. So so this paper really just looks at that kind of mathematics and how and just expands on it really. So although there is some worthwhile things to investigate here, it's not critical. Like we shouldn't get hung up on operators, obviously, and just sort of move forward. But you can make these kind of interesting vector graphs, which I've been working on more recently. So so that's that paper. And there's like work where I did later on. There's more of these vector kind of graphs. So then there's using those operators to generate like more surfaces in linear space, and then getting into the wave functions and all. A lot of this stuff needs to be redone and done like a lot better. But there's still like building on it from other perspectives, which are fine, like this Mexican hat, and then moving into the more complicated version, which is a sort of a wave packet form. But you can take the XNORD version of like the Mexican hat, and you get this kind of strange structure here, which has multiple dimensional qualities. And then you can take the parametric view of both the XNOR and XOR, exclusive OR, like, and to create this kind of thing. So you can imagine that this is like an interference pattern, and you know, the light coming through here creates certain interferences. This is the more complicated version with the exponential version, which kind of, this is the XNORD version of that. So you have these kind of waves coming in at an angle, and then nothing up here. But then I noticed that the results of the University of Warsaw, they were trying to look at the shape of a photon, and they came up with this. This was their theoretical prediction, and this was the experimental results. So it's pretty much in line with that, and that is based on Schrodinger's results. So I saw that here, similar structure, and so I just had to basically rotate this by 90 degrees, and that is kind of confirming with that. So that was just a little bit of a thing. I did a poster on it here, which is pretty much the same information, just laid out differently. That probably would have been the better one to use. But there were some issues though that I found, such as I wasn't actually able to find this paper on the journal that they were talking about. So yeah, so but I believe it's a real paper. I mean, yeah, I know it's a real paper. I don't know if it was removed, could have been removed because it was disproven. I doubt it. Like, they don't really do that. So maybe it was just badly indexed or something. I'm not sure. So that's kind of that on that front. So I'd like to maybe go back to here. So if we look at some of the, or maybe the earlier research I did, oh, sorry, every time I move my mouse up there, ignore. Yeah, it's a bit difficult to move my mouse. Yes, okay, so like these kind of things where this is quaternions, you know? So it's all made up of quaternion multiplication, which are, I suppose you could think of them as kind of outdated from the point of view of like relativity and tensors and all that. There's something I kind of like about them that I want to, especially from the point of view of the XOR and XNOR gates. So you can basically redo all of quaternion multiplication from the point of view of those two quantum operators. And then you wind up always with like two different shapes at the different dimensional levels. So this is the fifth dimension. I think I remember you were talking about the Higgs boson being 5-dimensional last time. I'd agree with that. This is like, for instance, what I got from the 5-dimensional quaternion XNOR multiplication, and that was like, so I had settled on that for the Higgs. So these kind of crystalline forms, though, we could possibly make use of them for maybe modeling of spin ices. Would be fun if it's possible. I don't know, because I do have some things that are getting a bit into that area. It should be just around here somewhere. Octahedral particles is kind of getting there. So if we look, so these guys are octahedral particles, and they come out of the sort of the, what do you call that? Like the negative space between these cubahedrons, or cuboctahedrons. It's been a while since I looked at it. So there's the two. There's the XOR quaternions and the XNOR quaternions. So when you're multiplying the two different ones together, and then you can start adding and subtracting them, and it creates a kind of interesting loop between the structures. So like a cuboctahedron will turn into a rhombi cuboctahedron, which will turn back into a cuboctahedron, and that's supposed to symbolize like an electron turning into a photon, turning back into an electron, that kind of thing, you know? So, and then these are the, that's kind of another octahedron. So to create, yeah, I don't know how I suppose if you were just going to make tetrahedrons, but not with this method, that's plausible. It's one way of doing it, because the moment I'm sort of just discovering geometries within this system, I don't always have a clear method of being able, like if you ask me to make a dodecahedron or something using this method, I'd probably wouldn't be able to do that. So so the other thing I was thinking about was along the lines of your quantum. Have you heard of these things like they're quantum crystals?
Heard about time crystals. Are they different from quantum crystals?
Yes, time crystals. So I'll have to look this up, but there's some sort of crystals, and they use channels, and then the particles move through the channels. I used it in a story that I had years and years ago. So you could like grow these huge crystals, and then essentially in the story it gets hit with a hammer and it just cracks. So the idea was that like if you were to like crack crystals in a certain way, you could like generate pathways that could be used as like computer circuitry. But yeah, I don't know. It was just kind of more of an idea in a story, but be interesting because obviously like each crystal would crack differently. You'd have, and it would be kind of random and chaotic. So, but I just saw this interesting concept. So then moving on from those kind of things, I've been looking into, well, a lot of it because I was able to take all of the 5-dimensional, 3-dimensional, and 4-dimensional and kind of squash them all into 4 dimensions, essentially normalizing them or getting the symmetry of them. And then so I'm big into explaining a lot of different aspects of the quantum world as 4-dimensional geometries, basically. So the best example, like some of the, so like QCD and gluon spin from a 4-dimensional perspective. So this is like just 4 spatial dimensions. Again, like 4 spatial dimension interpretation of the EPR paradox. That is with the, you know, that Stern-Gerlach experiment. There was,
that's about atomic magnetism, right? Stern-Gerlach, is it? More
yeah.
than
Well, you kind of send through these particles, and they go through an asymmetric magnetic field, and they either go up or down. So let's see, like either spin up or spin down. And then it has a lot of relationships to Bell's inequality theorem. So like if we look at that paper, it's like all to do with gimbal lock essentially. So the reason why if you send a particle through a north gate and then another north gate, there'd be no Z, is because according to this theory, from a it's almost like an analogy for the situation. It's like rotating something north 90 degrees and then north 90 degrees again, but using only Euclidean coordinates. So when you finally reach the top north pole of the system, you're gimbal locked. So you can only move in one dimension, which is like you can only rotate. You cannot keep going forward. You can move backwards though, and you can also move in the 4th dimension if you switch the coordinate system from Euclidean, like they are there, into, so there's the gimbal lock, into a 4-dimensional version, which is one of these. So you go up. Oh no, sorry, you start at the bottom, south pole, you move up 90 degrees, and now you're at the north pole, and now you're gimbal locked. But if you switch to the 4th dimension from there, you're fine. But if you were to switch back, you're going to notice a shift. It's going to, just because of the way the mathematics work, at least in this example. You could go like 40 degree, turn 90 degrees and then switch into the fourth dimension. And that is just an analogy for this setup here. So there's the first one, 90 degrees.
Is it like polarization? Excuse me.
Yeah,
is it
exactly.
like polarization?
Exactly. So
is it called a magnetic polarization or something? Or?
I think it is, yeah, possibly. That sounds about right. So there's your four-dimensional. Oh, this is what you need to change the Euler matrices into the four-dimensional matrices. So that's kind of just a neat little idea. And there's actually quite a bit in there about how that can be used for quantum entanglement and things like that. So that's kind of cool. That one's a little bit academic. They're kind of interesting results. And then I suppose the newest stuff here, hopefully this will cover most things. Like I did a lot of work into the 24 cell and the 288 cell, which I don't think I have in this, but it does have the 12th root of unity symmetry and probably a number of other symmetries as well. But this is like a lot of the data from that. So you have 48 particles. And where you get the 48 particles is like, there's 8 gravitons in this system. And the 8 gravitons are obviously conjectural. They haven't been discovered yet, but they mirror the other 8 gluons. And this is how gravity and SU3 strong force kind of combine, according to this theory. It's pretty loose, but it's a concept. So then we have all of the kind of, I don't know if you call them analogies, but homomorphisms, I suppose, between the quaternions, unit quaternions.
What's the diformism? What did he say? Excuse me.
Oh, homomorphism. So like an isomorphism.
Homomorphism.
Yeah, yeah, exactly. So unit quaternions, then we have the binary octahedral, I think, yeah, it's binary octahedral silo matrices. And then we have the just the octahedral, full octahedral group, symmetry group, and S8. And then you get into the polynomials and the roots of those polynomials. So one interesting thing that I'm working on, so this is the characteristic polynomial of this matrix, which is the matrix for this coordinate in the 24 cell, which is linked to, speculatively, to the graviton, the first of the gravitons. And so this, you know, we could start by investigating, like you can see that this polynomial is identical to this one. So, but this one is different. So it might be interesting to group them based on their different polynomials, which I haven't yet gotten around to. It'll also be interesting to add and subtract them, and even multiply them by their polynomial characteristic polynomials. So that's just kind of an area of research that I'm going to have to embark on at some point. That's a quick way of showing you without maybe a big diagram, but here you can see, like, these are the 48 particles. And so you can multiply them with each other based on the silo or the S8 matrices, which produces all of this. So here we have the quaternions in here, and then we have bigger symmetrical groups out here, which I'm not sure what they are, but so you can get you can play around with this and like apply it to the Higgs field and symmetry breaking. So I already did that with the 12th root of unity and the roots that I showed of the characteristic polynomials earlier. And you can get out a kind of something that's very close to the Weinberg angle. So you can start playing around with that number system to get the charges of the quarks. There's 1/3, then you can get 2/3 easily enough. And you can get the hypercharges as well by taking the inverse square of the Weinberg angle. And you can get the Gell-Mann matrices, gamma 8 one, which is a kind of important. It's a little bit different to the others. But then getting straight into, see, in this version, you have 4 Higgs bosons in this 288 cell theory, but you also have 4 components in, you know, the Higgs mechanism. They are slightly different. So, but really it's like trying to look for similarities between the mathematics in the Higgs mechanism with that of the 288 cell model that I just showed you. So we can do that. For instance, we can try and set this Phi A component to or Higgs doublet to one of the unit quaternions, and that would mean that it's equivalent to a tau neutrino and a T quark. So in that instance, so then we plug it into this equation, which uses the conjugate transposes, kind of like the Hermitian operators, I suppose, or the Hermitian matrices. And then we wind up with tau neutrino times a tau neutrino, which we can just run through here, find it down the left side. It's there somewhere. There it is. There it is. And then you multiply it by the other one and you get a Z boson. And then you do the same with the other 2, and you wind up in this instance, you get a photon. So Z boson and a photon, and those are the 2 particles that come out of the Higgs mechanism anyway, from the electroweak symmetry breaking. This one has 0 mass, and this one has a very large mass of 90 GeV. So then we can go on, and these are the mass equations for the bosons themselves. And we can relate those to unit quaternions, which can be related back to particles T quark and C quark. So that's very speculative about the idea that prior to the bosons becoming bosons, they were actually massless versions of these quarks, which I can't prove, but I just like the sound of it. Similarly, the mass equations of these electroweak fields prior to them, assuming there is a prior point where they don't have any mass, which is speculative again. It looks, once you put them into the matrices, it comes out with the same Silo matrix as a W plus boson, which is kind of interesting, but again, not concrete or anything. More speculation. These are the Silo matrices for the 4 speculative Higgs bosons, which could be which when added together to create this Higgs doublet, form this matrix, which just has a 1 here. So it just picks up this this Phi, which actually becomes the Higgs doublet, and it becomes this expression, which as far as I can tell is just the vacuum expectation value. So it's pretty weird, but it's quite interesting. I mean, that makes sense because you then have the mass of the Higgs, which forms, do I have the picture here? I do. This Higgs potential, and this is 5-dimensional, but obviously this is only the 3-dimensional picture, but because this 3-dimensional picture is creating the 1-dimensional, when you hike this up to 3 dimensions, we wind up with a 5-dimensional Higgs field. So even though—
This is what you're talking about, Mexican hat, right?
Yeah, exactly. So there's this potential up here is the Higgs value. Actually here it's put at 2, but in the equation it's 1.26. So that's in 100 GeV units. And here's your output expectation value of 2, which that should be like 246.22, but it's just shifted over. And okay, so that's a separate thing. But just to give you an idea of what we're talking about visually, right, so where are we? So that is where the doublet becomes a expectation value, and finally, sort of moving into the closing here, I think, I hope. Oh, yes. So out of that, you can keep playing this game, like, you know, doing everything we did before, changing up the phi terms, finding out which unit quaternions they match to, then finding those particles, then running the equation that we saw, equation 7, which has the Hermitian operators, to output something like, in this case, it goes tau multiplied by the anti-top quark gives a Z boson. And then here we have B squared essentially giving a Z boson. So the squared ones are kind of interesting because, like previously, although I don't think we did it. So let's just take a squared term, and then we obviously square root it. So that's the mass of that term, square rooted, divided by the mass of the B particle, which is the one where we actually want to get this hidden term here, which comes out as 559 GeV. So, and that works out at 3 times the vacuum expectation value minus the mass of the top particle. So that's kind of a strange result, and that's equal to the mass of the B quark, bottom quark. And we can do that again with the tau, and that means 5 times the expectation value plus the mass of the W boson plus the mass of the down quark, and all times the expectation value. So yeah, so it's kind of strange stuff, but I just like these little calculations trying to find patterns in the masses. A lot of these mass values are approximations, but they're close enough to be reasonably accurate, I find.
Does it correlate with the LHC measurements?
They're correlated with the standard model measurements, yeah. and also, like, if you look at the values that come out of the Higgs mechanism at the end, they're well off. They're like 40 GeV or more off. You know, they're saying like it starts at 38 GeV, it goes up to, you know, and I think the cutoff is like something like 80 GeV. But I'm not sure if that's entirely correct. But these are like, so for instance, there's 2 different equations here, and those 2 different equations give different results. One is approximately 4.48. You can see the rest of the number. And the other one is approximately 4.7, so forth. And so this value here is a lot closer to the down quark value that we know experimentally than this one. But they're still kind of in the same range. So really what's going on here is you can put in like any small particle, like the mass of the electron, the mass of the up quark, mass of a muon, like relatively light particles, to cause it and divide it by or have it as the divisor, and you're going to wind up with the same particle each time. So it's kind of like some sort of idempotent, you know, maybe it's not that significant, but it's just, these are
Can it
just
be called eigen identity or something? Is it like eigen identity type of thing?
Yeah, like idempotent means the same potency. So it's just always spitting out something kind of in the range. I think an idempotent probably needs to be the exact same number. I'm not so entirely sure about that. But so, okay, so we already looked at that. So that is kind of the general direction I'm headed in with this. So you can like do things like take the vacuum expectation value times the, what is that, the electroweak coupling value, and divide it by 2 cos the Weinberg angle to get an approximation again of the mass of the W boson. So it's, you know, I like that kind of stuff. I kind of like the numeric side of quantum physics. You know, the way there's questions surrounding the numbers, like of the fine structure constant and the ratio between the electron and the proton. things like that I find interesting. So I'm whereas some people are very into that. There's a guy called Unzicker. Do you know him? Real Physics, I think it is. He's kind of a bit.
What's the name?
I think his name is. I don't remember his full name, but it's Unzicker, I think.
Unzicker.
Yeah, I'll have to check that out. His full name. So
sounds kind of remotely familiar, but I'm not completely sure.
Right. Okay. So he's very into like the old work done by Pauly and these guys who are really interested in figuring out why the fine structure constant has the value it has. So they're all interested in really discovering why the constants are those numbers.
But they say it can vary. Now they said it's not that constant anymore.
Okay.
Fine structure. They're saying that actually it can vary based on like black or other things.
Yeah. Well, this is it. This is why I'm saying, you know, it's not a good idea. Like this Unzicker guy kind of seems to be putting all his eggs in the basket of these old masters, maybe if you can call them that, like who did some great work in the past and then seemingly got left behind. They were unable to adapt or adopt the quark model, for example. And when it came to the Higgs mechanism, you know, they were just, even Peter Higgs actually was completely against the idea of quarks for a long time, up until the 70s. But there's other people who are against what Peter Higgs imagined and the Higgs mechanism. And I think I'm just trying to kind of continue what is going on with, like, you know, finding these values and finding equations to derive these values, and then hopefully some pattern will emerge to help us see the path through the sort of jungle of equations that could manifest out of this situation. So that's really it. How am I doing on time here, Rajan? Any idea?
That's good.
I think we're good. So do you have any questions on that? Or any?
Yeah, Chris, excellent presentation. Thank you.
Thank you very much.
And you covered a lot of topic. I might say that I had to go back. I had few questions, but other things I had to, you know, I'm not completely sure about a lot of things, but you explained very nicely a lot of things as well. So it is, you know, it's a overall, you know, look at the whole aspect of the quantum crystal, you know, symmetry and other things. So one of the questions when I went through that I had was when you went to the XOR and X node, right?
Yeah.
XOR and X node measurements. That's one of the things. I think I will have more things later on when I go through that. And you said you can derive quaternions from there, right?
It's not so much deriving them, but it's you have the quaternion multiplication system already in place, and then you're kind of overlaying the quantum operators onto those structures. And then when you do the calculations in both XOR, which is what we usually do them in, and XNOR, then you have two different systems which you can then unite either in either methodology. But I usually go back to XNOR or exclusive, not exclusive, or whatever it is. And or no, sorry, go back to like our normal arithmetic, because I think so. The idea is that, like, let's say the double slit experiment is a really good example of this. So like when the particle is not being observed, it's sort of in like imaginary space in a sense. You know, it's like we don't know which place it could be flowing in through different directions, going in different directions. So, but it is only when it is detected that it kind of collapses into what our normal mathematics is. So the other kind of mathematics is trying to explain the non-observable aspect of it, but it is pretty speculative, I'd have to say. And also the results for XNOR arithmetic, when it's plotted, give different results to either XOR values or imaginary squared values, which is what is usually used. So it seems like, you know, it's like another kind of universe, almost like almost a mirror image of what's taking place here. And also some of the results, like when they are graphed, they're pretty odd results. So I kind of like that. I like the way it's unusual and sort of head scratching. But sometimes the results are quite concrete. Like, so instead of waveform, you're getting like a discrete geometric object, which, you know, I like the idea of. I'm not saying that a particle is like a tetrahedron or an octahedron or anything like that, but it's just like it kind of stands in for them, you know. It could be the shape of the field, or it could be like it is more likely a multi-dimensional object that's probably not even in the universe. But that's why you get into the whole, when you turn all the particles into four spatial dimensional particles, and you know, and then they're interacting, they have that fourth spatial dimension property, then they act in very in ways we would expect them to act. And it seems to explain a lot of the different things in nature, such as quantum entanglement. It has a bearing on that. Like I said, the Stern-Gerlach experiment, why spins, you know, symmetries, like why a fermion has to be rotated twice before it comes back to its start. And it does it all just by the inclusion of one extra dimension, spatial dimension. And it covers those and a lot more. So it could be quite a powerful theory. And even if it's not right on the specifics of like how it began, like even if those aspects need to be like forgotten about or removed, you know, the model itself could be quite useful just in general. Like someone else could take it and run with it, you know. But I personally, I like the foundations, but I mean, if you look at like a lot of the foundations of stuff like the Heisenberg, or what am I saying, the Higgs mechanism, where, well, let's focus on that, the Higgs mechanism. And there's like an operator in there that picks whether the fermion's going to be right or left-handed. And I mean, that's a remarkably contrived little construction, which, you know, works and gives you the correct answer. But you could just, you know, there's no way that is indicative of the reality of what's taking place on a quantum level. It's purely just a handy little way for someone to get from left to a right. That's how I see it anyway. I could be wrong on that front, but and I'm not saying that. So obviously there's some kinds of maths that just operates on that level in a very, I don't want to say simplistic or even simple, but it's not that simple. But you know, it's hard to know what the justification is for that from an actual physical perspective. From a logical mathematical perspective, it makes a lot of sense. But where is it in reality? You know, what is it describing? That's an interesting question, and I think I would like to hear more physicists discuss that personally. Because I'm more of an amateur here, rather. But then I mean, you know, if they're not asking these questions, so I'll have to do it for them.
Oh yeah. So yeah, I think connected with the chiral refraction we are talking about last time, I think kind of makes sense about the left or right-handedness because the chirality is bringing out the chirality in the Higgs mechanism. But the other one I had is the when we are talking about is in the overall sense, is particularly a condensed field. You know what I mean? So your
Yeah.
higher dimension, field is higher dimension. It could be like four dimension or 5 dimension.
Yeah.
And then when it condenses to 3D, is it the one that is becoming a particle?
Yeah. So in quantum field theory, I think
so then we are connected. You see that the connection between the particle and the field connects automatically. The wave and the field, I mean, is the wave. So the wave and the particle connection becomes automatic almost sometimes.
Yeah. Yeah. Just to say like a quick word about like where maybe contemporary physics is on the subject, that they think that a particle is the smallest part of a quantum field. So it's just like if you were to differentiate down the field to the smallest part, essentially that's the particle. So it's a bit of and it's also dimensionless. So it's bit of a ridiculous definition, I think. But let's go with it anyway for the time being. What I would do with like the particle, so like if you see, I don't know if I have a picture here. No. So like if you see, hang on a sec. Right, a tesseract, of course.
Yeah, that's another question I had. The next one is about tesseract. But
right, yeah, I'll just get.
I'm quite interested in that, the tesseract, because when I do some things, the tesseract comes in many times. The tesseract and tessellations,
Yeah.
There's some connection between the tesseract and tessellations. Tessellations are more, the transformation, what do you?
Sorry, I have to scroll down to the bottom of this page.
When you go from symmetry to another, you have tessellation, like steps can form. The crystals, when you go into dislocations, things like that, in the materials, you have, structures that, are like step structures, and you have the stacking faults and all those things.
Yeah.
And tessellations are essentially geometrically, when you rotate it or something, it changes the symmetry or keeps the symmetry. Is it invariant of the rotation? Things like that.
Right. Okay. So
is tesseract has invariance, or does it have no invariance in terms of rotational symmetry?
I think like I'm not really good on this subject, but I would say that from a 4-dimensional perspective, it is invariant. But from a 3-dimensional perspective, it is not invariant. That would be my interpretation of it. Because if you look, this cube here goes from the inside of this cube, the area is like a determinable amount. We can say it's like, I don't know, 3 cubed. But once it moves out to this cube out here, it's going to completely flip inside out, which means that the space all around the cube, the hypercube, is now completely filled with what was previously in this little area here.
Does it go inside out? Does it go inside out?
Yeah. But it just looks like it's going inside out. But from our perspective, that would be infinity. So that is the weird thing about it. But
what I'm saying, that inside one, the inside one, you have there. Yes. The inside one comes out and the outside one goes inside.
That's correct. Yeah. So you were asking then about fields and particles. So if you look at the one way to get around the crystalline, the fact that the crystalline fields that I showed you before have volume, whereas particles in QFT are dimensionless, is to say that, let's say this is 0, 0, 0, and this is, Cartesian coordinate point 0, 0, 0, and this is 1, 1, 1.
Mm-hmm.
Or no, actually, this is 0, 0, 0. This is 1, 1,
On the
1.
middle, yeah, right there.
Right, and this is minus, minus, minus. Well,
Yeah.
and then similarly with all of these, you know, 0, 1, 0, 1, and then minus 0, 1, 0, 1. So if you just subtract all of them, you get a dimensionless point here. So basically what I'm saying is you could collapse the whole structure down while rotating it in the fourth dimension.
Can you make it to 0 point?
Yeah.
Collapse to 0 point.
Right, and as it's collapsing to the 0 point, the dimensionless point that you need for quantum mechanics, it's also rotating, which means that by the time it reaches a completely dimension, so like all of these points are now in here, and all of the volume that is here and out here is now like totally outside of it, and like fills the entire universe. So that explains why certain objects would have like, you know, like why every atom in the universe is connected to every other atom via gravity and electromagnetism, for example. Whereas maybe the other forces get locked into what is being rotated into the very small area. That might explain the strong nuclear force and the weak nuclear force. But that wouldn't necessarily, but then we still have these volumes to contend with, and then, but we also have the fourth dimension. So it's kind of like, we're not looking, I think the examples I give with that, the XOR operators aren't really working in our dimension. They're kind of looking at it from a freer, higher dimension, you know, so, but we can describe all of this infinitely dense, infinitely high energy in a very small space, renormalization aspects quite easily with the same operators.
The inflation theory. But see, the IR Margulis formalism I had, the 0 point calculation, it shows the gradient. You have, you know, when you collapse this thing, then all these energies, so you have gradient. When I calculate, the gradients are very high. So it's a collapse point. It's like, it's all wrapping. Everything is wrapping, the dimensions are wrapping into the 0 point, right? Kind of.
Yeah.
All these are getting wrapped. So it has higher dimensions, higher symmetry, because it's actually the inner cube, probably outer cube comes into the inner cube, and then everything collapses. The outer cube tried to come out, but in that process, it's a harmonic motion. It collapses back into 0 point. And there are two variants. That's why our Margulis, our formalism says there are two variants. One of these 0 point, other one is micro black hole. So when it collapses, it can either form a 0 point or it can form a micro black hole. Because depending again, that's why a PDP circuit is important, depending on where the clock is, whether it's a magnetic thing you're sticking out or the electric vector is sticking out, you know, the surface. So surfaces are important in this. So how in the surface it is sticking out. Again, I think our PDP circuit, that's why it has wide-ranging application I'm putting in there. Many things we can, you know, and related to that, when you went through the quaternion, I was thinking about the PDP circuit. One specific thing is a fermion rotation. You said fermion has to rotate twice, right?
Yes.
Can we prove it from the PDP circuitry? If we can put something in that, that actually is one of the very partial verification. Because if you look at the PDP circuitry, which means that if I'm rotating, is it 90 degree twice, or I'm rotating twice 90 degrees? Is it pi by 2 rotation?
Well, totally. All in all, it's a 720 rotation.
Oh, it's a solid angle altogether.
Yeah, so like 2 360-degree rotations.
Yeah, it's called a solid angle, right?
Oh, yeah, I've heard that term. I'm not familiar with it.
Yeah, 360, 720 is called a solid angle.
Jeez,
360 is a circular angle, right? I mean.
Okay, right. I'll look into that.
Two-dimensional. It's a two-dimensional. Solid angle means three-dimensional rotation, whereas 360 is two-dimensional, aerial the surfaces, planar rotation.
Mm.
So,
but well,
so
like
720. Let me think about that. So if you are 720 rotation of, okay, the PDP circuitry right now is 2-dimensional. We are talking about, but it could be made into 3-dimensional. So, so we are saying, suppose it is rotating one. I mean, in this case, of course, if you are 2-dimension, twice rotation, one rotation, you will get the same result. If it is not 3-dimensional, if it's 2-dimensional, you get the same result. It will go back to, right? If I have electron here, I do a 360, I get back another rotation, I get back same. So I'm getting the same, but it's different. If you are talking about a PDP circuitry having 3-dimensional, right? The PDP circuitry as 3-dimensional, it's totally different story. So I'm saying that in that case, the North Pole and South Pole are here, South Pole North, but it is rotating. They have certain angle, so they are solid angle, like in the cube that you're talking about. So they may be on the diagonal of one cube and the diagonal of the cross diagonal of the other cube. So it's 3-dimensional, which means that if you are rotating twice, no, there is a phi angle. Okay, that's another thing. I don't know whether I will put it in this one. I calculated another thing called, okay, that's a whole new thing. Okay, that's a whole new thing from the gauge theory that we may have to postpone to the next paper. But what I was thinking, that's a larger thing, and that's helping me to figure out the gravity. Actually, the next one is talk more about the gravity. I'm deriving the gravity, actually, gravity gauge.
great.
It's unbelievable. It's all from first principles. It's nothing to, I'm not touching any of the other things. It's automatically falls one by one. It falls at the end with a standard model, or they have TF everything. But right now it's just our formalism, our paper that's gauging my physics formalism. Again, that's I'm going to present sometime, and that will be that may be a conference presentation. Like we can put a official thing if you can, but and then our paper comes after that. It uses all that. The main thing there, and another paper with the one Emery Taylor I'm developing, and he's coming back now. I was not sure, he was off for a while, but I think he's coming back. He has a paper, he has to wait some time. But where I derive from equivalency, I derive the velocity, gauge velocity I developed. And when I calculate from there, the omega, the angular momentum comes into picture, angular velocity comes into picture.
Cool.
So the angular, and I say that forms a functor, fiber bundle. And I describe that as fiber bundle assembly, functor with functor. So I have written it down, but it's connected to functors, fiber bundles, things like that. But the main thing is that omega is actually a summation, is a group. We have to put it as a group of theta rotation and a phi rotation.
Okay.
Okay. The theta rotation is the clocking. Okay. The clocking means that in the 2 dimensions, it works like a clock, right? It goes around.
Yeah.
The electron may be sticking out on top and then comes around, or a south pole may be coming on top when you rotate it, according to what we are given in the figure 1 in our paper. And there is another one called phi rotation. Phi is the spin. It's a spin rotation. It's like vertex. It's a spin inside of that. So each one, each assembly, like the North Pole and South Pole, it can spin, right? It can spin. It has a phi rotation. So if they are 3-dimensional, I'm rotating this way, like a clock, and that involves the monopoles and the particles moving around.
Yeah.
But when I talk about spin, it's in the other dimension, right? Let's say this is a North Pole and South Pole, the magnetic thing. So it's rotating this way in the orthogonal direction, which is a phi rotation. Okay. So we are already talking about 3 dimensions there. So from that point of view, if you look at the fermion twice, What it means is that, so the fermion, the first rotation, the 3-dimension, what is happening to fermion like electron? Let's follow the electron, right?
Yes.
Like the fermion. So the electron is suppose sitting here and I rotate it. When I rotate it, it's spinning also. The magnetic vector is spinning. So the phi is shifting the electron into the other dimension, away from the plane.
Yeah, maybe. I mean, Rajan, you were asking a question there about how to turn the gauge matrix into a 4-dimensional component. Like, I think we were kind of
eventually we have to do that, and conceptually we can kind of understand, but mathematics is highly involved.
I've kind of done that already, even in the. Does it appear in my last paper? It appears in one of them anyway. But so let's say you have a 4-dimensional, a 2x2 matrix. You can turn that into a 4x4. If you have a 2x2 complex matrix, you can convert that into a 4x4 real matrix. Yeah.
Okay.
So
that's something I can talk with you. I mean, you know it already, so we'll.
Yeah, it's really easy. I can show you that.
Okay.
And then I do it I've done it quite a bit, and then you can use those as your 4 dimensions, obviously. So like in this example here, there's a spin 2, there's spin 1, and here's spin half. So we could actually might be able to watch this. I don't know. So then with the 4 dimensions, right, it's really low quality. I can
but it shows the thing.
You got the idea. Yeah, I'll leave it at low so it doesn't tax my computer too much. So you can see it's rotating, and it needs to go around twice before it goes back to the.
So can we put our circuitry there, the PDP circuitry, and see if you have the program and see how it rotates, whether the twice fermion comes up, and you are saying if the fermion has to rotate twice in order to do what, to get a Higgs thing.
The fermion
has to rotate twice for what?
Well, no, it's just it's actually, how do you say that? It's a theoretical result based on the Dirac equation, I think.
Yeah, but it rotates twice. What happens if the fermions rotate twice? Does it form a quark?
No, it doesn't. I don't think it has a.
Or does it have connection with the proton or anything?
It doesn't really have a corollary, like a consequential aspect. It just is. It's just a fact of the geometry of the particle.
No, what is the resultant of that if we rotate twice the fermion?
Well, hang on a sec. Oh yeah, sorry, I've lost the. So well, it basically means well, there's a couple of things that it kind of entails, yeah. One, when you have like a spin half particle, there's a particular equation which shows that I think it's a complex number, and then you have the conjugate and the non-conjugate, just the normal complex number, and those two you put them into this equation. Again, it's like another kind of really, I'd almost call it hokey kind of Higgs mechanism like thing that doesn't make sense in reality. It's just an operator.
But how about quantum entanglement? Is it connected with the quantum entanglement?
Yeah, a little bit. So basically, supposedly, according to what I can kind of gather on this subject, it leads to the aspect where 2 fermions can't be in the same state in the same system.
Yeah, Pauli exclusion principle.
Exactly. So that is a type of quantum entanglement, because if one flips, another one has to, because they can't occupy the same state.